I'm going to walk us through the derivation of our line integral of a vector field, but we're going to do it using the application of work. This is probably one of the more common ways that I see this presented, and it's a really nice natural fit, and it leads very well to the equations and integrals that we like to get out of this. So I brought up a couple of tools for us, one of which, of course, is our integral from a to b of f of x dx. This f of x being our force, and the dx being a little bit of distance. So force times distance being work. Of course, we have our vector form as well of force times displacement. Again, force times distance, force times displacement giving us our work. Effectively, we're going to try and merge these two things together, but it's this second one, this vector version, that we're going to work with initially here. And the story that we get will be pretty much the same as a story of any integral. So if I want to know something about the work required to move my particle along this pathway through some particular field, what we'll do is we'll chop it up into little subintervals. You can see that's kind of been done here a little bit. And then we'll try and approximate how much work is being done on each one of those subintervals. From there, we can add up all those approximations and get ourselves a pretty good understanding for how much work is being done. As we've gone through our calculus, it's really the same. If you want a better approximation, take smaller subintervals. And if we want an integral, we can take the limit as the number of subintervals goes to infinity. So we will walk through that process using our vector form here again, work being F dot D. So we've got the force. Let's go ahead and take that, right? That's represented here on our graph. So we'll take our force vector to be some continuous force field Pi plus Qj plus Rk. So that's handled. We've got that taken care of in F dot D. Now we need the displacement component there. So with the displacement vector, we need two things. One, we need a direction, and two, we need a magnitude. The magnitude we'll get by looking at a small little section on one of our subintervals. So as I move from, say, Pi star here to this Pi point, what we have is a little bit of arc length in here. And that'll have some change. We can compute that or notate that as delta Si, thinking of S as our typical letter for computation of an arc length. So that gives us the magnitude piece of our displacement vector. The other thing, of course, we need is the direction. So that direction will come from using our unit tangent. And effectively, we just want to note that as long as this is a really small subinterval, the smaller that gets, the more and more linear it gets. In other words, we can approximate the direction that we're going at that point by using the unit tangent itself. It should feel a little like a linearization at a point. So we can use that again as the direction for our displacement component over here. So let's get that put together. So again, we're using the delta Si as the magnitude on some subinterval, and we're going to use the tangent, the unit tangent particularly, at a sample point, Pij, or Pi star rather, to indicate the direction. So we've got both direction and magnitude now, so I can piece together our work formula here for one of these little tiny segments. So it's F dot D. The force is going to be just notated here with F, and the displacement will swap out for delta Si times the unit tangent at our sample point, Pi star. And I'm just going to rearrange this one more time, and we'll write this as F dot T times Pi star times delta Si. So again, this is a little bit of work being done over this one particular segment. Of course, again, from calculus standpoint, the story goes you just add them all up. That gives you your approximation. Right? We would do it on this interval, this interval, this interval, all the intervals that we've set up. Add those up, and we get a good approximation from what the work would be. Take the limit of that sum as n goes to infinity, and of course the sum turns into an integral. So if we jump to the chase a little bit on this guy, what we get is that work is then going to be the integral over the curve C, and I'm going to write this out with just a little extra notation here just to make a few notes. We have our function of x, y, and z, our force, that is, and of course our unit tangent is also a function of x, y, and z. And our delta s will turn into a ds. And ds here being exactly what we think it would be from before. ds is the magnitude of r prime of t dt. And often you'll see books written out this way, the integral over c, just abbreviating some of that excessive notation, f dot t ds. So here's our work integral then. But as it turns out, this isn't really the end of the story for this particular derivation. Let's take c to be what it is. C is going to be some function r of t given as x of t, y of t, and z of t, parametrized by some vector valued function. And we know how to compute the unit tangent. The unit tangent t is going to be equal to r prime of t divided by its magnitude. And of course we also know how to compute ds. That is the magnitude of r prime of t dt. And the reason why I'm doing this is that we can actually replace up above here in our integral the t times ds and make a new version of this. We take the integral over the curve c of f evaluated at the curve, which would be f of r of t, times t, the unit tangent being again r prime of t over the magnitude of r prime of t. And now we take ds, which is the magnitude of r prime of t dt. And we get some good stuff that happens. R prime of t over r prime of t cancels. And so we end up with the following. Work being in the integral over the curve c of f of r of t times r prime of t dt. And this is generally a much more usable formula because, of course, when we're presented with one of these problems, we're often given whatever our force field is, and we're given some parametric form for the equation of the curve. So this gives us the ability to evaluate this much more directly. The only other thing I'll add here is that it's not unusual to take this particular expression, r prime of t dt, and rewrite it as its own little differential. So we would take the curve c, and sometimes they'll just write this as f dot dr, where dr is the r prime of t dt. So just pay attention to the notation on the differential. You'll see that this is a vector r in the dr, and that's telling you we're doing this r prime of t dt thing here. But ultimately this then becomes the simplest way for us to remember how to make a computation for work. And I'll just finish it off with one last equality, because we've seen this before in other lessons, and I drew an equivalence between this and the following integral as well. P dx plus q dy, where this is really the dot product of the function pq, which is the f for the force field, dotted with dx dy, or pq dotted with x prime of t, y prime of t, dt. So now again, we've got that r prime of t dt from that piece, and this is our f. So once again, getting back to f dot dr. We now have three different representations for computation of work. We have this form, we have this form, and of course we have this form. Again, from a usability standpoint, this is really how most of the calculations are done.